All right. So what we were talking about right at the end of last class. So last time we, introduced the idea of a game engine and what it's doing, and so far what we have in that list is the physics stuff, right? All this mathy stuff that we could do on our own, but since every single game needs some level of physics, well, at least our modern games, right? We go back to the really, really early games where you just had like remember Pong. Okay, well, even Pong had physics. Yes, I mean, you had to go back to basically when you just had like text, where there wasn't physics involved. Have any of you ever played those text-based games? I think I've mentioned them in some of my other classes called a MUD, multi-user dungeon. It's shocking how immersive they can be, even though there's like nothing on the screen other than just walls of text. It makes no sense. But once you kind of get used to where the important stuff pops up, it's like, I mean, it's pretty good. But in any case, physics, all these mathy things, is certainly something that a human being could write, something that we could incorporate in each of our games. But it's one of these things that it doesn't make any sense for us to go and rewrite that every single time, right? And so for those of you who've had we do it some at the end of 250 and then also into the 300 class when we talk about data structures, when we're writing stacks and queues and these types of things. We do them by hand in those classes to kind of understand how the underlying structure works. But then at the end of the day, it's one of those things where you kind of hope that there's already some sort of linked listy type of thing built into the language you're using, because if you need to store stuff and it's arbitrary in size, you don't know how big it's going to get, you'd like to be able to just use that rather than spend a half hour writing one, right? I mean, it just kind of makes sense. If you have these common tools that are available to you, that's where, or common tools that you need very often, you want them to be part of the language. And that's kind of the difference in these different programming languages between the core language. So here's the stuff that every single programming language has to have. And then kind of the larger library of objects or something that gives you access to stuff that you might need or is commonly needed on many projects, something like that. So Game Engine is trying to do the same thing. It's saying, look, here's the tools you're definitely going to need. You're going to need stuff to drag and drop and get your crap into the scene, because we certainly don't want to, draw every screen of our game on a pixel by pixel basis. Okay, that would suck. So we want to be able to take our little Mario guy, drag him onto the screen and say, there he is. Okay, and then maybe what we do is we put a ground in there, and we put him up a little bit above the ground at the beginning, and then we have him have gravity, and he just plops down to the ground when the game starts. Good to go. It would be really nice if that was something very simple for us to do, so we can focus more on the game mechanics, focus more on the things that make our game unique, right? The little, whatever strategy you're making, kind of a puzzle game or something like that. Focus on the puzzles, not on this stuff that, how does this wheel rotate? Because every single wheel is going to need to rotate in games, right? So we have those things built in. Well, so last time we were kind of talking about what aspects, when we kind of think about how games are displayed, what aspects matter. Okay, and the first thing we brought up was this idea of a frame rate. So if you go back to the early days, most of us in here, age-wise, probably did work on CRT monitors, right? The big ones at some point. Okay, if you've ever seen a CRT monitor on if you've ever seen it on like a video camera in a movie or something like that, what do you see? You see lines going down, right? What is that? What are those lines? Yeah, it's the refresh rate of the screen. Now, do you notice those when you're sitting in front of the monitor? Tell you what, your eyes do. Your eyes notice those. So it's less common today because of how our screens are built. We have what's called, what originally was called an active matrix screen. But now we don't have a visible refresh rate. The pixels are refreshed on a per pixel basis now. But back then, when you had something actually scrolling through the screen, effectively updating stuff as it was going, your eyes had to deal with that. And you had this idea, there's something called eye fatigue from using a computer. where your eyes would actually get tired from sitting in front of the computer, not just based on the amount of time, but because of the work it had to do to focus while the screen was refreshing. Make sense? Okay, so we have various things limiting us with our technology. We have how many frames per second can our monitor show, right? That's one thing. So maybe our monitor is a 60 hertz monitor. Okay, they go up to as fast as, I think right now the fastest monitor is like 240 hertz. Somebody might have something that's faster than that, but you know, if you see the same stuff discussed if you go and buy a big screen TV at Best Buy or something like that. You know, he's like, okay, well this TV's a lot cheaper than this one, and they look like, I mean, they're both 65 inch, they're both this, that, the next thing, and what's the only difference is this guy is 60 hertz, this guy's 120 hertz. And then you ask the person, you know, look, what's the difference? Why should I pay an extra $200 for 120 hertz? And they're usually going to say, well, are you a gamer? Or do you watch a lot of sports? You know, it has to do with that refresh rate. If you're watching a lot of sports, you're playing games where there's a lot of fast movement on the screen, on a slower refresh rate, you might see a shadow. Okay? If you watch football games on a screen that has a lower refresh rate, like 60 hertz, when somebody passes the ball and it's really fast, you might see a little kind of, you know, like almost a duplicate football behind it. You know, usually not the whole football, but maybe just a little piece of it, because the refresh rate wasn't able to catch up with, you know, if you're throwing that football and it, you know, you want to see it in smooth motion, and these guys are throwing it pretty fast, you're missing frames there in the middle where the ball used to be here, and then instead of being right next to it, it ended up being here in the next one. So you saw that shadow in between. So the idea is faster refresh rate on your monitor means more frames that could possibly be shown per second. Okay. Now, for many applications, it won't make a difference. You're not going to get a real big benefit with 120 or 240 hertz in Microsoft Word. You're not going to notice that, mostly because the text isn't moving. It's just kind of there. So, in any case, you have that limitation. How fast can the monitor even show frames? Then you have the limitation of our eyes. Okay, and not everybody's eye is identical, but we're in the ballpark of about 45 frames per second of what the human eye can see. Now, having said that, there is a caveat to that. We have pretty complex brains. So there's been plenty of, I don't know, I guess it could be called research, it's fair enough. Plenty of research that, you know, if you put somebody who's used to playing games, let's say, as an example, probably you could put anybody in front of a certain example, but somebody who's used to playing games, and you run a game at 45 frames a second, 60 frames per second, and 100 frames per second, they will be able to detect the difference, just from a smoothness perspective. It's more of a perception as opposed to what their eye can actually detect. There's some aspect of, you know, guy moving on the screen and something's missing. There's just not, on a faster frame rate, you're just not seeing that little tiny flicker. You know, almost that like shadow movement, but I'm telling you that it's going fast enough that your eye shouldn't be able to see the difference. But they can tell the difference between 60 and 100 frames per second. You know, there's some little perceptible aspect of that. Not huge, but it's there. All right? So that's another limiting factor. Then we get to our graphics cards, so our GPUs. And last time we were talking about cores, right? We were talking about your general purpose computers, CPUs, and how a fast one of those has maybe 6 cores in it or something like that, or, you know, with the hyper-threading or what's the new thing in the Ryzen chips, the Threadripper. They just keep coming up with like fancy names for it. It sounds cool, right? But I think it's just basically faking multiple cores. So, you know, our CPUs, our general purpose guys, can, you know, do 6 or 12 things at once. Let's say it's 12 cores. You know, 6 cores, 12 logical cores is with the hyper-threading, what they usually say. Okay, so that's the number of things it can do at one time. Now, is the capability of doing more things at one time always better? Like, is a 6-core processor better than a 4-core processor?
Speed.
Huh?
Speed also matters on how
Okay, how fast each core is, right? Okay, let's say that you have a 4-core processor and you have a 6-core processor, and both of those, every core is the identical speed across all of them. Is the 6-core better than the 4-core? Okay. Well, it depends. In a 6-core, if we forget about the hyperthreading thing, we can do 6 things at once. In the 4-core, we can do 4 things at once. It seems like, as you pointed out, that doing 6 things at once seems better than doing 4 things at once. Now, would you say that it's common for us when we're solving problems in real life that sometimes we are, some of us might say we're better at multitasking than other people, right? Some people say I'm good at multitasking. Other people say I got to do one thing at once. Otherwise, everything's lost. Okay. How often do you run into something where it would make a difference whether you can do 4 things at once or 6 things at once? In real life, practical things. It's not something you run into. Not that many things are divisible into that many pieces. The classic example in operating systems and hardware classes would be this idea of how many cores does it take to change a light bulb? Okay, so let's say we're racing to change a light bulb, and all of you together are on one team, and then I'm on the other team. And let's say I can change a light bulb at speed 10 because I don't have to get up on the ladder. And each of you can change the light bulb at speed 9, almost as fast, but not quite. But there's a whole bunch of you. Who's going to win? Who's going to win that light bulb changing contest? Me. So even though there's a whole team of you, only one of you can be changing that light bulb at once. And each individual of you is a little bit slower at changing the light bulb than me. So some tasks, as you point out, the clock speed makes a difference. And some tasks aren't going to benefit from those extra cores. So you have a 6-core processor, but at any point in time, maybe only 3 of them are actually doing anything, in which case the 4-core was plenty. Does that make sense? So it kind of comes back to that same example. Having more cores, especially if you're not giving up clock speed. Because that is a decision you have to make. If you're going to a 6-core processor and let's say it's running at 2.2 gigahertz each core versus a 4-core processor where each core is running at 2.6 gigahertz. If you're not going to often use those 6 cores, you might prefer to have less cores at a higher clock rate per core because it's going to benefit you more. They're faster. They're faster for the tasks you're going to actually be doing. So only if you're actually doing tasks on a common basis that require, that benefit, not require, but benefit from a lot of cores would it make a difference? Like what things in real life? So I win the light bulb, the light bulb game. So give me a game where the team would win. What's a task where the group of you, even though you're a little bit slower than I am at any task, every single task, I'm at a 10, you're at a 9. Sprinting. Moving stuff. Picking up stuff, right? So let's say you have we're at the university, and it's we're this time of year, kind of transition into the fall, right? So leaves are going to start falling. We're going to have leaves all over campus. Okay, so now we're going to have a contest. So what we're going to do first of all, so we're going to duplicate campus. Easy enough. Okay. Now we're going to have a race. I'm going to rake the leaves around campus, and all of you are going to rake the leaves around campus. Now I can rake leaves at speed 10. Each of you can rake leaves at speed 9. Who's going to finish raking those leaves first? By a lot. Right? I'm going to still be around one of the first parking lots when you guys are finishing up. Because that's a task that can be divided among multiple people in this case, or multiple cores. All right. So now let's take it to the computing world. What are common tasks in the computing world that really benefit from multiple cores? Huh? Okay. Why do you say games? The answer's wrong. But let's get your rationale first.
Well, I thought because you have the physics to be computed by this guy.
Okay, in fairness, let me re-ask the question a little bit cleaner. What aspects in our computer would benefit from multiple cores in the CPU? Because you're 100% right from GPU cores. Okay, well, and we're kind of segueing toward GPU cores next, but would benefit from more CPU cores, because this kind of goes back to the statement I made a few minutes ago and also last class that if a 6-core processor can do 6 things at once, now we have to decide what is the nature of those things that it can do. And a CPU we can just think of as being general purpose. It can do all sorts of things, where a GPU is more special purpose. It can only do a very small number of things, but it does them really well. Okay, so your answer is correct if we're talking GPU cores. Okay, but now I want to talk about CPU cores. So why might more CPU cores help us in gaming? They don't, or at least to a limit. A couple probably do help.
I remember I used to have like tutorial supports to open up all the GPUs, but it never, all the CPUs work while playing the game.
Mm-hmm.
Don't work because when I launch something, my CPU just works. The other ones are idle.
Yeah.
I don't know why, but.
Well, it comes down to how many tasks are happening at once that require kind of generic computing in a game. Probably 2 cores would benefit you in a game, because there are aspects where maybe a game is having kind of 1 core dealing specifically with user input, and then maybe another core might be doing a lot of networking stuff. So because you wouldn't have as little, I guess let's call it lag as possible. Because otherwise, the magic trick that our CPUs do is fake us out, right? They're so fast that even though only a single core CPU, even though only one thing is actually happening at once, they happen so fast that we can sort of kind of do 2 things at once from our perception, right? But if we're talking about a real-time game, where you're playing against people from all over the world or something like that, and that if I have a little bit slower process than you, that fake out time means something, right? Even though I'm maybe not noticing that 2 things aren't actually happening at once, since my machine's a little bit slower than your machine, I might not be able to compete. If we're at equal skill level at the game, let's say, we might not be able to compete fairly with each other because you have an advantage with your computer hardware. Okay, and that's what you see. Now we have this movement for like e-games, right? Esports. So people are playing, video games as if it's a sport. It's become a big thing now. And at the competitions, they, generalize the hardware. So all the computers people are playing on are the same hardware, as opposed to at home when you're playing with somebody over the internet. Your computer very likely is at least not identical to the people you're playing against. They might have a different graphics card, different processor, different memory, blah, blah, blah. So when we're talking about games, in terms of general purpose problems we might need to solve at one time, we're certainly not going to take advantage of a 6-core, at least not in today's games. Okay? Because really, we maybe you divide today's games that are mostly, we can say a lot of the games today are online. So there's communication between some server that then distributes it out to all the game clients. Let's just, for generic purposes, say a couple of cores would probably benefit us. 1 for our user input, and then 1 for the communication with the server. Right? More cores than that is not going to really benefit us. And you're saying, like, when you're playing your games, you notice that you have a bunch of cores and only 1 of them is really firing. Right? Yeah, I mean, so basically, you've got all this money into this multi-core processor that's sitting there idle. Okay, we actually had historically we had a really funny punchline. Once again, Apple is the butt of the joke. So this was before Apple went to Intel processors. So this was in the days where Apple had PowerPC processors, and they had a chip called the PowerPC G4 chip. So they had the Mac Pro that had a G4 processor in it. It was like 1.4 gigahertz or something like that. And it was considered a really, it had this technology in it called AltaVec, which was kind of like before hyperthreading existed, it was kind of like a hyperthreading thing, but AltaVec just sounds mysterious, right? And there was actually something was really, it was some very specific application it was really, really good at. There was this thing that some buddies and I, we used to have competitions. So I think the site's still up. It's called distributed.net. And you've seen these various applications where it kind of uses your idle CPU time on your computer to do other tasks. One of them is like called SETI at home, help search for aliens, right? So your CPU is sitting there. I mean, and that's kind of the interesting thing. We spend all this money on our computers and our processors sit idle like 95% of the time. Most of the time, they're not doing anything. Now, that gets skewed a little bit with today's game addiction. Where if you're spending 18 hours a day playing games, you're going to be using your CPU a lot. Okay, but in general, under normal workloads, your CPU is not doing anything most of the time. It's just ready to serve you when you do need something. So while it's sitting there doing nothing, you might as well benefit humanity by searching for aliens. Or in the distributed.net thing, what it did is it was stress testing encryption algorithms. Okay, so when a company or somebody came out with a new encryption algorithm, where the way to crack it was like to brute force guess the password, that type of thing. They would have 64-bit keys, 128-bit keys, 256-bit keys, gigabit keys, whatever you needed. Your computer had to try this key, then generate the next key, then generate the next key. Did this work? Did this work? Did this work? Did this work? And then what they did is they distributed that problem across a whole bunch of computers. So you can decide that you want your computer to participate in that game. So your computer would check into the key server, grab a collection of keys that were yours to try, and then you would try to crack the encryption with that key until you finally got the key, and then they got the answer. And there wasn't even really any true data encrypted, like worthwhile data. It was more about just how long, in a situation where a piece of information was actually encrypted, how long would it take an army of computers to crack that code? Because that could happen, right? So your performance in that on a single machine basis was keys per second. How many keys per second could you test? And AltaVec, the same clock speed with and without AltaVec, could test something like 6 times more keys per second. But then my buddies and I, we would go and we went to all the computer labs and we put hidden processes in the this was back in Windows 3.1 days. So it would run on all the lab machines. So we had this rule where you weren't allowed to erase somebody else's. So you were trying to find these extra machines around campus to hidden stealth install your stealth install your client with your credentials in it. So it was working for you for your account on distributed.net. But AltaVec was very good at doing that. And one of the funny punchlines with that was an encryption algorithm called triple des, which is actually was a government project. And the government, basically said, "Oh, this thing is not crackable. It would take a zillion years," and because the nature of security has changed. Before you can just say, "Oh, well, we'll use a 64-bit key, and that means there's 2 to the 64th unique keys. It's a big number." Okay? And if you have one computer trying that, it might take hundreds and hundreds of years, especially by computing power back then. Even today, it would take a long, long, long time where at the very least, the data that was encrypted is no longer useful. If we're encrypting missile codes or something like that, and they're only good for the next 24 hours or something, and you crack it in 19 years, it's not going to be all that useful to you. But then we have this idea, once networking became a thing, now you can distribute the problem across a whole bunch of machines. That's an issue. So now you got to make these security algorithms even more, larger keys. And what's big enough? Well, how many computers are working on it? Kind of becomes a thing. Well, the government had really, said, okay, we're going to do this triple des thing, and government was saying it's uncrackable, just uncrackable. would take something like lifetimes, many, 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 many lifetimes. So I think Distributed.net cracked it in something like 2.5 minutes. And but this other group made a machine specifically for cracking triple S. They made a hardware-based machine that was built specifically for testing keys on triple S. This isn't necessarily dissimilar to like the Bitcoin world, where we have these machines called ASICs, application-specific integrated circuits, that are built specifically for solving the Bitcoin mining problem. They suck at everything else, but that's the thing they do. All right, and I think that machine did it in like 92 seconds. One computer. Okay, so now that kind of throws the whole distributed problem. I mean, basically, triple S failed out the gate. They fixed it and did some other things, but in any case, when we're dealing with CPUs, we have to think about the nature of the problems they solve. And it's a very general purpose problem that a CPU can solve. Now, when we talk about GPUs, this is where we start getting into physics stuff. We're thinking about games. Okay, when we're thinking about games, there's a lot of stuff happening on the screen at once. Now, historically, we would think about these things as polygons. How many polygons are on the screen at one time? Because everything was kind of typically drawn as triangles on the screen at one time. Now, that same thing is true today, just they're a whole lot smaller, to the point that they all look smooth. But if you go back into some of the, if you played like, what vintage would, well, certainly like Nintendo 64. So if you played the Nintendo 64 console, that was kind of that first video game console that you started seeing like the games that tried to be 3D, and they were very all the character models had edges, right? You could see the triangles that were built to design the guy, because you had that frame rate issue. This frame rate issue has been around forever. So what's the coolest 3D graphics that we can show while still maintaining a frame rate of, let's say, at least 30 frames a second, for the gamer to be able to think that the stuff is happening smoothly. You get the Super Mario World, let's say, on, I think that was Nintendo 64, was the first Super Mario World. That game, you put that on running at 3 frames a second, people are going to be far less impressed. Okay, so that's why Mario didn't look more realistic than he did. He looked pretty good for Mario. He's a cartoony guy, so you can get away with it, right? But point is you can see the edges on the character models, because the characters were made up of a lower number of polygons. And when we get into Unity, one of the things we'll see in the asset store sometimes is this thing called low poly. So low poly characters, because a lot of times we might be using somebody else's assets, and here we're going to be using 2D stuff. But in the next course, we'll be using 3D stuff. And if you're taking, I know a couple of you are taking the 518 class, we're going to be doing 3D stuff this semester with virtual reality. So, the idea is you might choose from a performance perspective, like, my game doesn't need to be super realistic. So from a performance perspective, I'm going to choose low poly models that somebody made, because I know that's going to be easier on the graphics card to display on the screen, which then will make the game more usable across multiple machines. So like when they made Angry Birds, for example, Angry Birds is a 2D game, although I think there's a 3D Angry Birds now that I've kind of seen. I don't know if it's out or I've seen previews for, but there's something. There's a 3D. They've gone 3D. But in any case, the first Angry Birds was a 2D game. And it was like medium poly, because not that much stuff there was only a certain number of things that were actually moving on the screen. If you think about Angry Birds, a majority of what you saw on the screen was just a picture, right? Only a couple of things were actually moving, so they can increase the polygon count a little bit, especially considering that most people are playing it on smartphones, that the graphics in these is decent. Even though it's not what this machine could do, and this machine isn't what a desktop machine built for gaming can do, it's enough to show that many polygons at a smooth frame rate. All right, so you kind of have to decide who your audience is from the perspective of the machines they're likely going to be playing the game with, and what those machines at the, let's call it, lowest common denominator are capable of, and then target that from a asset perspective. So you either have lower quality assets in your game or less assets. There's going to be some number of polygons that you'll be able to show on the screen at once before it starts drastically impacting your frame rate, because you're going to start dropping frames because it isn't able to keep up. All right, and that's something that just happens with kind of trial and error at first. Nothing we're going to be doing in here is going to really require the greatest GPU in the world, but we want to have an appreciation for how it scales to that. When they come out with the next Battlefield game or something like that that's trying to look really, really, realistic, they're using incredibly high poly counts, because I don't know if you've ever looked at another human being, but there's not a whole lot of edges, right? We're made up of a whole lot of polygons. That would actually be I'm sure somebody's done it. I wonder what the poly count is. I'm sure there's a poly count that the human eye could detect. Because that actually gets to, it's related, so let's talk about that too. We'll use the phrase that Apple came up with, but most companies now have an equivalent. How many of you have heard of the Retina Display? So, on the iPhones, they have the Retina Display. This is usually a PPI or a DPI problem. That's pixels per inch or dots per inch measurement. So here we go. Pixels per inch. Okay, so the idea is if you go back to, and what I would show people in the early days of the message from somebody. If we go back to the early days of iPhones, let's look at the transition with the iPhone 3G to the iPhone 4. 3G did not have Retina display. The iPhone 4 did. What I would do is I would take people to the number pad on it, like you're making a phone call. Look at the number 2. On the iPhone 3, you would actually see the individual pixels that made up that 2. You could see them with your naked eye, no problem. The iPhone 4, same screen, couldn't see the pixels. So now the pixels were there, I promise you. But there were so many pixels clustered together. They were so tightly bound that your eyes couldn't detect the individual pixels. They played a trick on us. They all melded together. Make sense? So now you get these screens that come out, and they all measure in pixels per inch. Now it's at the thing of well, do we, if you have, and pixels per inch is also a measurement of how far away you're using it, because the original Retina displays on iPads, you actually, if you got it close enough, could start seeing the pixels. Okay, they said it was a Retina display from a normal viewing distance. You couldn't see the pixels. Okay, but now all of our devices, the screens have gotten so good that at the point where everything becomes blurry, you can't see the pixels. So do we ever need more pixels per inch? You could say no, not until we get the Terminator eyes, right? We have these upgraded eyes. Well, now we have some other things that drive that. That's screen size. So the bigger the screen, the more obvious the pixels are. So you go to a baseball game or something like that, and you're looking at the Jumbotron out in the outfield, and you see the screen up there. I mean, some of these actually, some of the new stadiums have 4K screens that actually it might be hard to detect. But in general, you can see the pixels to some level, right? I mean, it's not as crystal clear as your laptop screen might be. Well, your laptop screen is squeezing those pixels into a lot smaller space. Where on that giant screen, well, an inch isn't all that big relative to the size of the screen. So you're going to start seeing the pixels. Okay, so seeing actual pixels is one aspect of the quality of graphics. The number of polygons is another aspect of graphics. Now, the more pixels that make up a graphic, the bigger the graphic, right? The more space it'll take. The bigger, the heavier that frame will be. If you think of a single picture of your screen, looking at something. If you're running a game at 4K, so that's like the when you hear about these new consoles coming out, the new Xbox One, and it's going to bring the true 4K gaming. What does 4K gaming mean? It means that the resolution that you're playing the game at is 4K. That's 4 times 1080p. Okay, in terms of number of pixels, it's like 4096 by 2560, something in that ballpark. In terms of the resolution of your screen. Okay, and now you got to consider, well, how many pixels, pixel clusters do you use to get them close enough so that you can actually see stuff, or you see that you won't see the pixels. Well, so the more pixels you have on the screen, and then a Retina display with showing 4K is showing a lot of pixels, a lot. So if we do something like let's just do 4,000. Let's see, it's 4096 by 2560. I think that looks right, doesn't it? Pretty close. So that is 10. This is if it's just 1 pixel per spot. So this is the worst, or this is the easiest 4K picture to show. So that's 10,485,760 pixels per screen, per frame. Okay. Now we've decided that we want at least 45 frames a second, right? At least for the human eye to be convinced. Really, 60 is probably our real minimum. So let's multiply that by 60. So now we're at 629,145,600 pixels. Now each pixel is going to have some color associated with it. Okay. Usually color is going to be either 24-bit or 32-bit color. So let's go with 32-bit. So that's times 32. So that's the number of bits for a single second of gameplay. So divided by 8 gives us bytes. Divided by 1024 gets us kilobytes. Divided by 1024 gets us megabytes. Divided by 1024 gets us gigabytes. So 2.3 gigabytes of uncompressed data to show 1 second of gameplay at 4K. It's a lot. It's a lot of data. So to be able to push, and that's at 60 frames a second. That's 4K at 60 frames a second. That's the amount of data that your graphics card has to be able to push. And that means it has to process those frames and display them.
Something else going to follow.
Yeah, I mean this is the current problem with 4K. And you go down from 4K, it's still a problem. We're dealing with a lot of data that has to go at one time. Okay, so if you think about your computer as just having all these interstates in it, right? Some road has a speed limit that's too slow. That's keeping you from, this is why nobody wants to go to West Bend. Okay? There's no fast roads that go there. Okay? If you had an interstate that went to West Bend, it would be an 8-minute drive. Instead, it's a half-hour drive because you're on country roads and stuff like that for half the drive. Okay, it's just there's no same thing with brown deer. Nobody wants to go to brown deer. Or where else is? Yeah, they're good examples. There's just no good ways to get there. You got to put a monorail in. Wouldn't that be good? We need a good monorail here. You've been on the Disney monorail, right?
No, lucky, just fall apart. The whole county.
Well, not if you go north-south. Just chill on 45, or 43 rather.
And I have a friend I hang out with in Cedarburg, and then I have to go to Veck one for school.
All right, so lots of data, right? Lots and lots and lots of data. So that gives us an idea on what we're kind of dealing with when we're trying to push stuff to the screen, and that's why we need super fast graphics cards that can do all this heavy lifting for us if we want to drive things at these super high resolutions at frame rates that are good. Now you get to this point where how much resolution is actually too high of resolution? Or stuff on the screen, like if I'm driving my computer screen at 4K versus 2K, let's say, for screen resolution, at 4K, I mean, when I go from 2K to 4K, the physical dimensions of my screen do not change, correct? But when I go to 4K, I am putting a whole lot more stuff on the screen at one time. So if the physical dimensions don't change, but I'm still fitting more stuff on the screen, that means everything gets smaller. Now, when you're younger, maybe having a lot of small stuff on the screen is okay. But as you get older, having the small stuff on the screen is no longer a benefit. But even when you're younger, there is a such thing as too small. You can't read it anymore. So just going to higher and higher and higher resolutions doesn't necessarily get us anything. We're starting to run into the limitations of the human body, okay, and what we can comfortably view. I guarantee if you're looking at a 4K picture versus a 2K picture, with the same pixel density, you're not going to be able to tell the difference. The only time you're going to see the difference is on a large screen. The bigger the screen, the higher resolution will be the perceived better quality. Okay, so if you're watching a movie on a 65-inch TV in your living room from 15 feet away, you might notice the difference between 4K and 1080p and 1K. Because you're far enough away and the screen is big enough that you'll notice a crispness difference. But if you're on a little laptop screen, and you're sitting, a foot from it, all of a sudden things are just smaller. is what it is. Go ahead.
Does that help in the field of view if you have a higher resolution?
It can if the screen is big enough, or if you're in VR and it gives you a wide enough angle, because now it can spread the stuff across a larger resolution. So that when you're actually looking at what's just directly in your field, that might actually only be 2K. Even though it's capable of showing 4K across. But what you're focused on isn't extra small. You're using the real estate to show more stuff, even though you're not directly looking at it right now. And some of the new technology, especially going into to VR stuff, we're starting to deal with eye tracking, where the helmets are trying to track where your actual pupils are looking. That way, it's making sure that part of the screen is getting fully rendered, where stuff over here will be blurry. And you can actually see that even in real life. Well, you can definitely see it if you wear glasses. But in real life, if you are looking straight ahead, everything should be fairly clear. If you kind of sort of try to peek out of the sides, just take quick little glimpses, you'll see that it's blurrier. Because your brain isn't processing all that data because it's not in your direct field of view. If you turn to it, then your brain's going to start processing it. And it's just efficient, right? Like, for instance, my brain does not need to process what's going on in the field house right now. Okay? Even though clearly I have eyes behind my head. Well, actually, it's probably eyes by my ear. Field house that way, right? Yeah, so I have ear eyes. So, and it can see through the walls, obviously. Okay, but I'm not wasting my brain power processing those images right now. Because they're not in my field of view. Nowhere near my field of view. Okay. So, makes sense. General purpose processors, they serve a purpose, but not so much a graphics-based purpose. GPUs have a lot more cores. I mentioned last time that if a really good CPU is like a 6-core thing, a GPU, let's call it a really good GPU, might have 2,000 cores. 2048, something like that, number of cores. That's a lot. So now you might say, whoa, wait a minute. So my CPU over here, my Intel Core i7, has 6 cores in it, You're telling me that this new graphics card I just bought has 2,000 cores in it? Well, now we're back to that. How many cores does it take to change a light bulb? Okay, but now we're back to this idea of what kind of tasks can benefit from a lot of things at once. A bit ago I asked the question, we gave a real life example. If we are raking the leaves around the university, having a group of people doing it will be faster than having one person do it. Okay, up until a point, unless the one person is just ridiculously fast. Like I might be able to rake leaves around the university faster than if you gave like little mini rakes to a bunch of 1-year-olds. But they're not going to spend a lot of time raking. They're going to learn a low performance raking unit because they're going to start playing with leaves and they're going to fall asleep. They're going to be crying. It's going to be this whole fiasco. Okay, but in computing world, if we're thinking about common tasks for, and this is something that maybe some of you have experienced before. Not that any of you have ever downloaded like a movie from the internet that wasn't quite in the right format, that your machine that you wanted to watch it on was able to display was the wrong codec, maybe. Yeah, so you downloaded an AVI and you needed it in MP4 format or something like that. Okay, if you're let's say it's an hour and a half show, and you want to convert it on your laptop. So let's say it's a 2-core processor mobile laptop thing. Hour and a half show might take a couple hours to convert from AVI to MP4 if it's on 2 cores. Now let's take one of our Mac Pros down there that has 12 cores in it. That same movie on those 12 cores, even if the cores were the same speed, will probably take something like 3 or 4 minutes to convert that video. Because converting the video conversion is something that is divisible. You can divide the work up across all those processors, taking full advantage of them. Same thing's true for video rendering. A lot of video and graphic stuff benefits from multiple processors because you can deal with different quadrants of the screen at once with different cores. Okay, so if we have 2,000 cores in our graphics cards, those cores can be working on all sorts of different parts of the current frame that's getting ready to be displayed. That allows it to keep up. That allows it to show more polygons because it's got a whole bunch of mathematicians doing the math to get those things on the screen. Make sense? So up to a point, the more cores, the better. Now I guarantee though that if you're playing Angry Birds on an NVIDIA 1080 Ti, let's call it our top of the line graphics card right now, you're not going to see a perceived improvement in performance over whatever the stock graphics card is on your budget pleaser laptop you got from Best Buy a year and a half ago, or 3 years ago for that matter, because that game's not pushing it. You don't need 2,000 cores to process those frames. All right, but GPUs, these are physics workhorses. They do a lot of math, and they are what keep up our frame rates. Okay, but usually it's if you're a gamer, one thing that maybe hasn't changed over the years, so if you've been PC gaming for a while, you might notice that the frames per second that you're after, let's just say it's 100 frames a second. So you're chasing 100 frames a second. That's been the same for the last several years, that 100 frames a second. What's changed? The quality of the graphics in the games. So the game makers keep pushing their games for the current hardware to let you maintain that same frame rate that you've been happy with. So fine, you can go back and take your modern graphics card and try to run a game from 5 years ago, and you're probably going to get a pretty good frame rate from the top of the line graphics card. But who cares? I mean, if you're getting 300 frames per second, it doesn't matter. Our eyes can't see that. We were saying at the end of class last time, what's the benefit of having 300 frames per second versus 90 frames per second if our eyes can only see 45 frames a second? It's not the common case, it's the worst case. If you're getting 90 frames per second and you walk into a busy part of the game and that 90 drops down to 30, you notice. If you're at 300 frames a second, you walk into a busy part of the game and it drops down to 160 frames a second, no problem. You're not going to notice because it's still way above what you can perceive. That's where the heavy-duty graphics cards come in. Not on the average case, but the worst case. They help you through the rocky parts of the game where there's lots and lots of stuff going on. Okay, questions about any of that? We kind of understand the purpose of these different things as it relates to our games. Okay, now I promise you that in well, at least for us in here, frame rate's not going to be a concern. All right, we're not going to be creating these really in-depth games that have professional level graphics at super high resolution and all this stuff. What we're learning is a set of tools using industry standard stuff that would allow us to then go into a company that has a team of a team of designers and things like that, as well as a target platform that has the higher resolution stuff, as well as somebody else has probably imagined the game and told you what features it's going to have. So as a developer for that, you're going to be like the person in charge of making, the dude be able to do some game mechanic or you shoot something and have it look realistic or that kind of thing. All right, so you're going to be working with models and animations that were given to you, as opposed to you being the one that's creating them. Now, if you are interested in the animation side of things, which I'm of the opinion that you should understand all the parts, decide which ones you actually like, and then focus in on that area, but you want to understand how all this stuff works. I would encourage you to look at the animation classes from Dr. Wall. He gets into some pretty good depth. I think they're actually adding a third animation class now that'll take you into farther stuff, and he knows way more about that stuff than I know enough to not want to do it, is what it comes down to. All right, so now the two game engines and in the kind of the modern competition, we have two game engines that are like in competition, let's say. So we have Unity and we have Unreal Engine. Okay, now Unreal Engine, this was a game engine that came from a game called Unreal from many years ago. It was considered to be a pretty good game. And they ended up open sourcing it and making it available to everyone. Now, there's a lot of game engines beyond these two that exist. Some companies, usually they would be the big video game companies, probably have their own internal game engine that they've worked on that's a proprietary piece of software for them. Now we're getting to that idea of we mentioned earlier in class today about this idea that why reinvent the wheel? If you're going to need physics in every single game, why rewrite that every single time? Well, sometimes there might be a performance benefit to doing it in a very specific way. But let's call it 95% of games using a stock physics engine is probably fine. Okay? So there's going to be game engines out there that are not available to the public, okay, because they're proprietary pieces of software that live within those companies. In terms of our public-facing game engines, that what would be called an indie developer. So we're independent developers, and you might be writing a game and releasing it on Steam or something like that. These are probably the two engines you'd be picking between. Okay? There are some other ones but these are the two big ones. So we're going to focus on these. Now, we picked Unity in here, and we want to understand why. So if we kind of talk about maybe pros and cons of these different guys. So Unity I'm going to say until recently was weaker on graphics. Now I'm not going to actually put it on here because their new version actually has an updated graphics engine piece that brings it basically on par with Unreal Engine. Okay, Unity has C#/JavaScript scripting. So those are your two languages of choice for writing your scripts in the game. And we'll talk about the role of scripts in the game. That's actually the programming part, okay, where you write the scripts. But those are your two languages you have a choice between. Unreal Engine has C++ as well as visual scripting. All right, so some people go into Unreal Engine specifically for this visual scripting thing, which is effectively you don't actually write any code. It's all drag and drop stuff, but that does give you some limitations. But you can accomplish quite a bit with that. So it's not a huge limitation. I would say there's been many games that have been shockingly complex that were done 100% with visual scripting. Okay? So now you look at this and say, well, who are we going to give the advantage to when we think about scripting? Well, I definitely, I think JavaScript scripting up here is dumb. You might as well use this C# as a more powerful, it's a more robust language. Fair enough. But there's a lot of people that were already familiar with JavaScript that would just keep using JavaScript. But we'll be using C# with Unity in here. Versus C++. Now, there's nothing wrong with C++ on the Unreal Engine side, but C++ is an older language. Less people today know it in general. Now, people who have been in the gaming industry for a long time likely are more familiar with C++ than your average computer science person. Now, some universities still teach C++ classes. You've heard me in my my classes kind of advertise that the language doesn't matter. Right? Programming is the skill set. The language you actually are using to write that software is insignificant. So if you get into C++, it basically looks like Java. It basically looks like C#, but it's the older version of those two. So you sometimes run into some things that look a little weird because they're actually things that were common in C++ that have evolved out of those languages in our modern version of them. That doesn't mean they're broken. In fact, I usually have a conversation in the class about Java where we talk about structs versus objects. So C++ had supported something called a struct, which was effectively a collection of name-value pairs, but it didn't let you have methods. Well, then you compare that to a class, an object in Java, which allows you to have a bunch of name-value pairs. You can have integers and strings and stuff like that, but it also allows you to store functions. So then so what Java did, though, is they took away structs with the understanding that, oh, well, if you just need to store name-value pairs, you don't actually need functions. Well, just create a class that only has name-value pairs in it. Don't write functions. So they would say that a class with only variables defined in it is equivalent to a struct. It only allows you to have variables defined in it. Anybody remember who's been in that lecture? Why they're not actually identical? I got one bucket over here that's capable of holding name-value pairs. I got another bucket over here that's capable of holding name-value pairs. This guy is also capable of doing a little bit more, but I chose not to use it for that. I chose to stop at name-value pairs. So aren't these two things equivalent? On the surface, they seem like it. There's one caveat. It deals with passed by value versus passed by reference. Objects are passed by value. Objects are passed by reference, by address. Now, structs are passed by value. So if you're in C++ and you write a struct and you pass the struct into a function and you change the contents of it in the function, the original did not change because it was passed in as a copy, as a value. In Java, if you have your fake struct that you wrote as a class, you pass it into something, you change it, it has changed. So they don't act identically. Now, is that the end of the world? As long as you know that they don't act identically and you take the proper precautions, fine. right? No harm, no foul. Okay, but C++, I think, would be less beneficial to you today than it's probably ever been. Because we certainly, even in the gaming world today, are starting to transition over to C# as the main language, especially as we are getting into more and more reliance on game engines like Unity and Unreal. We have fewer and fewer games that are being written from scratch, where you implement all the pieces and things like that. And historically, those were probably done in C and C++ for nothing more than speed. So you traded off performance for platform dependence. When you write something in C and C++, you're kind of marrying yourself to whatever platform you designed for, which not the end of the world, because you probably were designing for Windows, and that's where most of your customers live. It's fine. You're not losing out on that much. Okay, but in terms of what's going to be most beneficial moving forward, I believe that becoming an expert in C# will benefit you. And since all languages are effectively created equal, if you got into a situation where you needed to learn C++, it wouldn't be a big deal. Most of your knowledge transfers directly over, and then you'll just learn a couple of new things, enumerated types, type defs, things like just a couple. Literally, it's a handful of things that make somebody who's never seen a C++ program kind of look at it and say, that's weird. It's pretty much the same thing. Okay, let's call it a month learning curve for just the little details that you only have to deal with sometimes. All right, so one difference between them, I'm not a big fan of the visual scripting from a programming perspective. I think the visual scripting is actually great from the perspective of, let's take a younger person who maybe hasn't had any programming experience, getting them into game design, because as we're going to see in here, and it's going to be, I would say for most of us, I mean, I'm sure several of you are bigger gamers than I am. I play games, but I used to play games a lot more. I don't really play the modern games very often. So as somebody who's a diehard gamer today, you're going to have these ideas about the stuff that games have in them that I don't. Okay, you advertise to me that the fact that games exist doesn't matter, right? But that's okay, because programming is programming. Okay, so we're going to rely on somebody who's let's call it an active gamer to give us those ideas of, oh, we want Mario to do this kind of thing. It's like, okay, well, now as programmers we can say, oh, I don't know why you want to do that, but fine, you want him to jump and get up on that and land, and he might die from the spinning fire thing. Okay, let's write that. Okay, for no good reason other than that's the problem we're solving, and that's okay. All right, so understand there's kind of two sides to game programming. One is deciding what we're going to do, and the other one is just being a programmer and saying, okay, here's the tool I have, and let's do that. Who cares, right? So that's the problem-solving aspect of it. So I will, as we get into some more advanced stuff, I'll be relying on the audience, specifically our heavy gamers. I do light gaming still, but we'll rely on our heavy gamers to give us some good ideas for what we want to implement. Okay. So for a younger developer who maybe hasn't done a lot of coding, this visual scripting thing gives them a lower barrier, a lower point of entry to get into the thing, follow tutorials, be able to do the drag and drop stuff, and not have to deal with the stress of getting over the programming hurdle. And most of the programming hurdle stress deals with intimidation, right? When you see a wall of code, now that most of you have had some various levels of programming experience, you realize it's not as bad as maybe you originally thought. Okay, but at first it's intimidating, because when you first get into computer science, you've never had programming before. The picture that's in your head is you're just going to be looking at a screen of zeros and ones. The 2-button keyboard just tapping it out. It's like, oh, it's going to be like a magician, right? It's that type of thing. Now that we've gotten into it, we realize, well, some of you might think programming is more fun than others, but, well, it's not that. It's not just a wall of zeros and ones. Okay, so I think that from a modern day programmer's perspective, C# is the better tool. Or at the very least, it's not a worse tool. So I think worst case, we can call it a tie. All right, from a scripting perspective. Now we have to start thinking about the skill set we might get out of this. Some of you are taking this class because you want to learn as much as you can about the kind of the various technologies that are out there, and it might even be the type thing where it's like, okay, let's find out what game programming might be like, and then decide, is that kind of the industry I want to get into, or do I want to be more on the business application side of things, or do I want to switch my major to art? Okay, whatever, you got to decide what gifts God gave you and roll with it. Not all of us were built for the same stuff. Obviously I could have gone into computer science or become an Olympic runner. I had to choose. So it's, I do have incredibly fast burst speed, like 0 to 60 in like never, but yeah, when I used to play tennis before I broke my back, I was always a pretty good sized guy, but I played Division I tennis, and I would get to balls that people never would think I would get to. So because I was 6'5", maybe 230 when I played tennis competitively, but that's still a pretty good sized guy. But I could get up to speed and get to the ball quickly, like if somebody hit a drop shot or something like that. But then the point was over. I'm not going back. So I got one burst in me. It's kind of like a bear. Bears can go, can't they go like 55 miles an hour? And then they sleep for a day. They're done. All right, so we kind of think about what we can apply Unity or Unreal Engine to. So we kind of want to look forward a little bit and look at kind of some of the features of these guys. Now, Unreal Engine has become quite popular, but something we're noticing here over the last year, let's say, is more and more, let's call it, important players are jumping on the Unity bandwagon. So as we're starting to think about, and this is true for other aspects as well, but focusing on the virtual reality and augmented reality stuff, which is becoming big. Here in September, Apple's going to make the announcement for the new iPhones, and it's going to be all about augmented reality. Apple has released this thing called AR Kit, Augmented Reality Kit, which we're going to be messing with at some point here in the department. But this is where things are going. Okay, well, Unity. So we kind of think about our different pieces of technology we have in here. So this guy, Unity, supports VR. Unreal Engine supports VR. Actually, let's be more specific with this. We're going to call this Steam VR. And Oculus VR. Unreal Engine supports the same two. So that means if you're writing stuff for either the HTC Vive or the Oculus Rift, either one of these game engines is acceptable. All right, so now we have a piece of equipment down there called the Microsoft HoloLens. I think that's it. HoloLens, which is a augmented reality helmet, which is going to be, I think, a thing. Probably more of an industrial tool than a consumer tool. They're expensive. You can't buy them yet. We can only get it as a developer kit, but it's cool. You can only write stuff for HoloLens using Unity. Microsoft is effectively partnered with Unity, and you're going to see when we install Unity on your machines, which I'll have you do here for next class. You're going to see that, especially if you're doing it on Windows, it comes with Visual Studio. So Microsoft and Unity have partnered. All right, so you can do stuff for HoloLens using Unity. Similar, the new mixed reality stuff from Microsoft, where you're going to start being able to use Windows 10 using effectively a VR helmet. So we have one of those in the department as well. I have a mixed reality helmet that's a developer version. And the difference between mixed reality and our virtual reality is if you want to set up VR, you have to put these sensors all over the place. So it's a little bit of a time to set it up. Once you get a room set up and you're not going to move it, it's fine. Mixed reality, the helmet has cameras on it. So even though it looks like VR, you're completely immersed in it, you don't have sensors to set up. The camera detects your room. Now, the trade-off though right now is a little bit of accuracy. I would say VR is pretty precise, where mixed reality is kind of precise. Close enough for right now, and I'm sure it's going to get better. But in any case, as we go down this, we're going to start seeing more and more stuff living on the Unity side of things. Now, I don't want to 100% guarantee this because I'm not positive, but I believe that ARKit from Apple is also only on Unity. I'm not positive, so don't quote me on that. I will try to get that answer for you officially, but it's definitely on Unity. I haven't seen anything that talks about it on Unreal Engine, so that's what I'm basing that off of. Okay, so let me kind of save this for now. What I'm going to have you do for next class is go to Unity, do a search for Unity 3D. It's going to take you to this website called unity3d.com. And it is kind of a big download, so you're going to want to do this when your machine's plugged in and have an internet connection, maybe do it overnight or something, depending on the speed of your connection. You're going to want the newest Unity here, the 2017.1, which is the one that'll kind of make you download. If you want one of the older ones, you kind of have to kind of snake around to get to it. So now whether you're on a Mac or a PC, you're going to download Unity the same way, but Macintosh people, and I think I have a link for Unity up on Blackboard. I think I take you directly to the download page with it. But in any case, you're going to go to get you want the personal edition. Is it going? Go. Where's my download? Well, whatever. Somewhere on here is the download for personal edition. And you'll get that. So it's going to download it'll download a installer, which is pretty small. And then, here we go, download Unity. It'll download an installer, which is pretty small, and then that'll do the installation, which is a fairly large installation. So you'll try personal. It'll come here. You click on this guy to agree, then download the installer. Okay? If you're on a PC, that's all you have to do. Double click on the installer. It'll start doing all the things. It'll ask you at the beginning what target platforms you want to do. Use the default. I would also encourage you, since we might do some deployment on this, choose Android and iOS. Both of those. It's on Windows as well. It supports both of those. So, because I think it's going to be, it'll say PC is the default, and then choose Android and iOS, which we may or may not use. And on the Windows one, it'll also install Visual Studio. I think when it first pops up, it actually gives you a little error message saying, I can't detect whether you already have Visual Studio installed. So it'll install it for you. Okay, so don't worry about the error message. It's normal. Just hit OK. You will need it. Okay. Technically, you can use something called Mono Develop. It is not as good for this. And I'll explain why when we get to it, but you want Visual Studio, trust me.
I can't install on my Linux. The whole Unity. Mono is on Linux, but it's not altogether.
Mono is not unusable. Mono is fine. What it doesn't give you is the function completion, which is you're going to see is going to be beneficial. So you can do it. You're not going to be at a humongous disadvantage, but for the 2 or 3 functions that we're going to use pretty often, you'll have to go copy and paste the function definition and just paste it in there. Okay, not the end of the world, but it's, that's really the advantage it gives you. Now, if you're a Mac user, I also have the link up on Blackboard. Also, download Visual Studio for Mac. It does not come with Unity, but we'll configure your Unity to use it. I'll show you that next time. All right. So for Tuesday, I'm going to expect everybody to have Unity completely installed in their machine, and we're going to make it dance around the screen next time. Sound good? All right. I will see everybody on Tuesday.